Hello and welcome to Deep Sleep Seas. Maybe you've had one of those long days where your mind just kept going, or perhaps you're simply ready to let everything soften and fade. Either way, you're in the right place. Your body knows how to rest. Let your breathing find its own quiet rhythm and feel the weight of the day beginning to settle, like something heavy and warm draping gently across you. Beneath the ocean, there are valleys carved so deep they dwarf the Grand Canyon, hidden in darkness where corals glow softly and life moves in slow, patient rhythms. Tonight we're drifting down into these hidden places, the deep sea canyons, where the seafloor has been shaped over millions of years by forces as gentle as settling sand and as powerful as underwater avalanches. You'll hear about creatures that make their own light, about valleys that stretch for hundreds of miles, and about ancient currents that still flow today, quiet and unseen. But before we jump in, if you enjoy learning about our oceans, you're welcome to let us know where you're tuning in from and what time it is for you. It's always fascinating to see how far our stories reach. And if these quiet ocean journeys help you unwind, you're always welcome to subscribe so you can drift off with us whenever you need. Now let your body grow a little heavier as we begin. Imagine standing at the edge of the ocean, looking out across the water. The surface seems almost flat, interrupted only by gentle swells and the occasional whitecap. But beneath that deceptively simple surface lies a landscape as varied and dramatic as anything on land. In fact, the ocean floor contains some of the most extreme topography on the entire planet. Mountains taller than Everest rise from abyssal plains, trenches plunge deeper than any terrestrial valley, and carved into the continental margins, where the shallow coastal waters transition to the deep ocean, are the submarine canyons. Scientists estimate there are approximately 9,477 submarine canyons on Earth. Let that number settle in your mind for a moment. Nearly 10,000 of these massive underwater valleys scattered across every ocean, cutting through every continental margin. They cover about 11% of the continental slope, creating a vast network of channels, tributaries, and pathways through the underwater landscape. And yet, despite their abundance, despite their size, despite their importance, most people have never heard of them. They remain hidden, out of sight, and largely out of mind, known primarily to the scientists and explorers who study them. These canyons are not small features. Many extend for hundreds of kilometers from their heads near the continental shelf, all the way down to the abyssal plains in the deepest parts of the ocean. Their walls can rise thousands of meters from the canyon floor, creating vertical or near-vertical cliffs that dwarf any cliff face you might see on land. The canyons themselves can be several kilometers wide at their mouths, narrowing as they cut deeper into the slope. Picture standing at the rim of one of these canyons. If you could, you'd be looking down into a chasm so deep and dark that no light from the surface could reach the bottom. The walls would disappear into blackness. The scale would be almost incomprehensible. The Grand Bahama Canyon, for instance, has walls that rise nearly 5 kilometers from canyon floor to canyon rim. That's higher than any mountain in the continental United States. The Congo Canyon stretches for 800 kilometers from the mouth of the Congo River all the way across the continental shelf and slope, making it one of the longest submarine canyons on Earth. The Monterey Canyon off the coast of California extends for more than 470 kilometers offshore, with walls that reach over 1,700 meters high in some places. These are not minor indentations in the seafloor. These are major geological features, comparable in scale and grandeur to the most impressive canyons on land. But here's what makes them even more remarkable. Unlike terrestrial canyons, which we can see and photograph and hike through, submarine canyons remain largely invisible to us. We know they're there because we've mapped them with sonar, sending sound waves down through the water to bounce off the seafloor and create detailed bathymetric maps. We've explored a tiny fraction of them with submersibles and remotely operated vehicles. But the vast majority of these canyons have never been seen by human eyes. They exist in permanent darkness, under crushing pressure, in cold that would freeze you solid in minutes. They are among the least explored places on Earth, right here on our own planet, hidden beneath the waves. The formation of submarine canyons has puzzled scientists for decades, creating debates and discussions that continue even today. When they were first discovered in the late 19th and early 20th centuries, when improved depth-sounding techniques began to reveal the true topography of the ocean floor, the obvious assumption was that they must have been carved by rivers during ice ages. when sea levels were much lower than they are today. This made intuitive sense. After all, we can see how rivers carve canyons on land. The Colorado River carved the Grand Canyon over millions of years. Why shouldn't submarine canyons have formed the same way? And it's true that some canyons do align with river mouths, preserving a direct connection between terrestrial and marine systems. The Hudson Canyon off the coast of New York connects to the ancient path of the Hudson River, the same river that flows past Manhattan today. During the last glacial maximum, about 20,000 years ago, sea levels were more than 100 meters lower than they are today, a drop of over 300 feet. To visualize this, imagine the entire continental shelf exposed as dry land, with the coastline pushed far offshore. Rivers that today empty into bays or near the shelf edge would have flowed much farther, cutting across the exposed shelf before reaching the ocean. The coastline extended much farther out during these glacial periods. In some places, it was hundreds of kilometers from where it is today. Rivers flowed across what is now the continental shelf, potentially cutting valleys that would later become submarine canyons. As the seas rose with the melting of the great ice sheets, the Laurentide ice sheet covered much of North America. The Scandinavian ice sheet covered northern Europe. As these ice sheets melted, releasing their water back to the oceans, sea level rose relatively rapidly in geological terms, flooding the continental shelves and drowning the river valleys that had been cut across them. This explanation works beautifully for some canyons. The Hudson Canyon clearly shows evidence of having been a river valley during lower sea levels. So does the Monterey Canyon, which may have been carved initially by an ancestral version of what is now the Salinas River. The Mississippi Canyon was clearly influenced by the Mississippi River, which during glacial times would have flowed directly into what is now the Deep Canyon head. These shelf-indenting canyons, as they're called, cut across the continental shelf and align with major river systems. They're among the largest and most dramatic submarine canyons on Earth. But this explanation can't account for all submarine canyons. Many are found at depths of 3,000 meters or more, far deeper than sea levels ever dropped, even during the most extreme ice ages. The geological and oceanographic evidence is very clear. Sea levels during glacial maxima dropped by about 100 to 130 meters at most. They did not drop by thousands of meters, yet submarine canyons extend to depths of 4,000 meters and more. The Congo Canyon reaches depths exceeding 4,000 meters. The Perth Canyon off Western Australia reaches depths of 4,000 meters and contains what's described as the world's largest plunge pool. These depths were never above sea level, not during the most recent ice ages, not ever in the time since complex life evolved on Earth. Others show no connection to any river system whatsoever. They're called headless canyons because they don't extend back to the shelf edge to capture river flow. Instead, they begin partway down the continental slope, with their upstream ends hanging in mid-water, so to speak. Some are found along coastlines that have no major rivers at all, coastlines that are arid or that drain such small watersheds that no significant river reaches the ocean. Yet the canyons are there, often just as deep and extensive as canyons fed by rivers. So if rivers didn't carve all these canyons, what did? The answer lies in a process that is uniquely marine, uniquely powerful, and rarely witnessed by human observers: turbidity currents. These underwater density flows, these avalanches of sediment-laden water, are now recognized as the primary mechanism for submarine canyon formation and evolution. They carve granite bedrock as effectively as rivers carve terrestrial canyons. They transport sediment over vast distances. They shape the morphology of continental margins and build enormous sediment fans in the deep ocean basins. Understanding turbidity currents is absolutely essential to understanding submarine canyons. Without turbidity currents, most submarine canyons wouldn't exist. And so, as we continue our gentle descent into the realm of these hidden valleys, we need to understand the forces that created them, the invisible processes that continue to shape them today, the submarine avalanches that have been sculpting the ocean floor for hundreds of millions of years. Turbidity currents are one of the most dramatic and powerful phenomena in the ocean, yet most people have never heard of them. They are, in essence, underwater avalanches, dense rivers of sediment-laden water that rush down the continental slope at remarkable speeds, carving and shaping the seafloor as they go. Understanding turbidity currents is essential to understanding how submarine canyons form and change over time. Imagine sediment piling up at the edge of the continental shelf. This sediment comes from rivers, from coastal erosion, from the gradual weathering of rock, from the remains of countless marine organisms that have died and settled to the seafloor. It accumulates slowly over time, building up in layers, becoming thicker and heavier. Eventually, something triggers a failure in this accumulated sediment. It might be an earthquake, shaking the seafloor and destabilizing the sediment pile. It might be a storm, stirring up the water and adding just enough extra weight to cause a collapse. It might be the gradual accumulation of material, finally reaching a critical threshold. Or it might be something more subtle, a small slump, a minor disturbance that sets larger processes in motion. When the sediment fails, it doesn't just slide slowly down the slope like a mud flow on land might. Instead, it mixes with seawater to create a dense, turbid slurry that is heavier than the surrounding water. This density difference is crucial, fundamental to everything that follows. The sediment-water mixture begins to flow downslope under the force of gravity, just like an avalanche on land flows down a mountainside. But because it's denser than the surrounding seawater, it stays close to the bottom, following the contours of the seafloor, accelerating as it descends into deeper water, channeling into valleys and canyons that focus the flow and increase its power. Turbidity currents can travel at astonishing speeds that boggle the mind when you consider that this is happening underwater, with all the friction and resistance that implies. Measurements in Monterey Canyon have recorded flows moving at speeds up to 700 centimeters per second, which translates to about 16 miles per hour, about 25 kilometers per hour. Other canyons have recorded even faster flows, with some turbidity currents reaching speeds of 43 miles per hour or more, approaching 70 kilometers per hour. To put that in perspective, that's faster than you might drive through a residential neighborhood. That's faster than many boats can travel. And these aren't small trickles of water, not little streams carrying a bit of sand. These are massive flows, sometimes carrying cubic kilometers of sediment, volumes measured not in cubic meters, or even cubic hundreds of meters, but in cubic kilometers. 1 cubic kilometer is a billion cubic meters of material. The Bed 5 event we'll discuss later grew to 162 cubic kilometers of sediment. That's an almost incomprehensible volume of material, all moving together down the continental slope and across the abyssal plain, powered by gravity and its own density, carving and sculpting as it goes. These flows are powerful enough to erode solid rock. They carve through sandstone and shale. They abrade away limestone. They can even erode granite, given enough time, enough flow events, enough sediment particles acting like sandpaper on the canyon floor and walls. Even hard granite bedrock, among the strongest rocks on Earth, can be carved away over time by the constant abrasion of flowing sand grains, by the physical impact of cobbles and boulders tumbling along in the flow, by the sheer erosive power of fast-moving, sediment-laden water. The canyon deepens with each flow, cut a little deeper, eroded a little farther. The canyon widens as the flows undercut the walls, causing them to collapse and adding more material to the flow. The canyon extends headward, eating back into the continental shelf like a river valley in reverse, growing upstream rather than down. This creates the characteristic V-shaped profile seen in most submarine canyons, particularly in their upper reaches. The cross-section looks like the letter V, with steep walls converging to a narrow floor where the flow is most concentrated and erosion is strongest. Smaller turbidity currents might carve shallow channels, tributary channels that feed into larger canyons. Larger ones can excavate enormous volumes of material, fundamentally reshaping the seafloor in a matter of hours or days, doing work that would take thousands or millions of years if it relied on slower processes alone. A single large turbidity current can move as much sediment as a river might move in decades or centuries. The Colorado River, one of the major rivers of North America, transports about 15 million tons of sediment per year in modern times, though this has been reduced by dams. A single large turbidity current can transport comparable volumes in a single event, lasting just hours. What's particularly fascinating, what really captures the imagination of scientists who study these systems, is that turbidity currents are self-reinforcing to a point. As a current flows downslope, it can erode more sediment from the canyon floor and walls, picking up material and incorporating it into the flow. This additional sediment increases the density of the flow, makes it heavier, makes it sink more strongly toward the seafloor. And this increased density makes the flow move faster, accelerating down the slope under stronger gravitational pull, and moving faster increases its erosive power, its ability to pick up and transport even more sediment, which increases the density further, which increases the speed further. Scientists call this positive feedback mechanism ignition. It's an appropriate term because it captures the idea of a sudden acceleration, an explosive growth, a relatively small initial slump, maybe just a few 100,000 cubic meters of sediment, can ignite into a massive turbidity current that grows to many times its original size as it races down the canyon. The current feeds on itself, growing stronger and larger and faster as it incorporates more material until it becomes a true monster of the deep, an underwater avalanche of terrifying power. But this process has limits, important limits that prevent turbidity currents from growing indefinitely. Eventually, the sediment concentration becomes so high that viscous forces begin to dominate. Think about honey compared to water. Honey flows, but it flows slowly because it's viscous, thick, resistant to flow. As a turbidity current picks up more and more sediment, it becomes thicker, more viscous, harder to move. At some point, typically when sediment makes up a very large fraction of the mixture, the flow becomes too thick, too dense, too viscous to move efficiently. It's no longer a fluid flow but something closer to a debris flow or a mud flow, moving more slowly and less dynamically. At this point, the turbidity current begins to slow down, and as it slows, it starts depositing its load of sediment, losing its cargo particle by particle. The coarsest material, the gravel and cobbles and coarse sand, settles out first, dropping to the seafloor as the flow can no longer keep it in suspension. Then the medium sand, then the fine sand, then the silt. Finally, the very finest clay particles drift down through the water column, sometimes taking days or weeks to settle completely, floating in suspension, slowly filtering through the still water, eventually coming to rest on the seafloor in a thin blanket of mud. This creates distinctive layered deposits called turbidites, sedimentary deposits that are the calling cards of ancient turbidity currents. Each turbidite shows a characteristic sequence with coarse material at the bottom grading smoothly to fine material at the top. This is called graded bedding, and it's one of the key signatures that geologists use to identify ancient turbidity current deposits in rocks that are now on land, rocks that were formed underwater millions or hundreds of millions of years ago and have since been uplifted by tectonic processes to become mountains. Scientists have only recently been able to measure turbidity currents directly. For most of the 20th century, these flows were known primarily from their deposits and from indirect evidence like broken submarine cables. The famous case was the 1929 Grand Banks earthquake off the coast of Newfoundland. The earthquake triggered a massive turbidity current that flowed down the continental slope, breaking a series of submarine telegraph cables in sequence as it passed. By noting the time each cable broke, scientists could calculate the speed of the flow. It was traveling at speeds up to 43 miles per hour. But they couldn't see the flow itself. They could only infer its existence from the damage it caused. More recently, scientists have deployed instruments directly in submarine canyons to measure turbidity currents as they happen. The Coordinated Canyon Experiment in Monterey Canyon, conducted between 2015 and 2017, used dozens of instruments at 7 different locations to track at least 16 separate turbidity current events over an 18-month period. The data revealed that these flows are more frequent, more complex, and more varied than anyone had previously realized. Some turbidity currents were relatively gentle, dilute flows of fine sediment. Others involved massive movement of the entire seafloor, remobilizing layers of sand and creating a dense basal layer that drove the flow forward like a traveling wave. The instruments themselves told a story. Some were buried completely by sediment. Others were moved hundreds of meters down canyon from where they'd been deployed. Heavy equipment sometimes traveled farther than lighter instruments, defying expectations. The seafloor changed dramatically between surveys, with some areas experiencing meters of erosion while others saw meters of new sediment deposition. All of this happened in the space of a single flow event, lasting just hours or days. One of the most remarkable findings was that major external triggers like storms or earthquakes are not always necessary to initiate turbidity currents. Many flows occurred during periods of relatively calm weather and no seismic activity. Instead, they seemed to be triggered by more subtle processes. the slow accumulation of sediment reaching a critical threshold, seasonal variations in sediment transport across the shelf, or even the failure of sediment that had been deposited by previous flows. Submarine canyons, it turns out, are much more active than we thought. They're not static features, carved long ago and now stable. They're dynamic systems, constantly reshaping themselves through the regular occurrence of turbidity currents. Consider the Bed 5 event, which occurred in the Agadir Canyon off the coast of Morocco about 60,000 years ago. This turbidity current started as a relatively small submarine landslide with a volume of about 1.5 cubic kilometers. But as it flowed down the canyon, it grew explosively, eroding and incorporating sediment as it went. By the time it reached the abyssal plain, it had grown to a volume of 162 cubic kilometers, more than 100 times its original size. It traveled more than 2,000 kilometers across the Atlantic seafloor, moving at speeds exceeding 50 kilometers per hour, eroding everything in its path. The resulting deposit covered an area the size of Germany. Events like this are rare, but they demonstrate the incredible power of turbidity currents and the crucial role they play in shaping the ocean floor. Every submarine canyon on Earth has been carved, at least in part, by these underwater avalanches. The deepest cuts, the steepest walls, the most dramatic features all bear the signature of flowing sediment, and this process continues today. Right now, at this very moment, turbidity currents are flowing down canyons somewhere in the world's oceans, invisible beneath thousands of meters of water, reshaping the seafloor, transporting sediment from the continental margins to the deep sea, continuing the work that has been ongoing for millions of years. The geological record preserves evidence of ancient turbidity currents going back hundreds of millions of years. Rocks that formed as deep-sea sediments in ancient oceans have been uplifted by tectonic forces and now form mountain ranges on land. Geologists studying these rocks can identify ancient turbidites, the deposits of long-dead turbidity currents that flowed down submarine canyons in oceans that no longer exist. The graded bedding is still visible. The sedimentary structures are preserved. Even the fossil assemblages, the remains of organisms that lived in and on the ancient seafloor, tell stories about deep-sea environments from the distant past. In California's coast ranges, rocks called greywacke form much of the landscape. Greywacke is a type of sandstone, but it's unusual sandstone, what geologists sometimes call dirty sandstone. It contains not just sand grains, but also substantial amounts of mud, giving it a gray color. And it shows graded bedding, with each layer grading from coarse at the bottom to fine at the top. These rocks are ancient turbidites, deposited in a deep ocean trench off the coast of an ancestral North America hundreds of millions of years ago. The ocean has long since closed, consumed by subduction. The trench has been filled and uplifted, but the turbidites remain, now forming mountains and hills, testament to processes that continue in today's oceans. Similar rocks are found around the world wherever ancient deep-sea sediments have been uplifted. The Alps contain turbidites from the Tethys Ocean that once separated Africa from Europe. The Himalayas contain turbidites from ancient oceans that closed when India collided with Asia. Japan, New Zealand, the Andes, all contain rocks that record ancient turbidity currents. The process is fundamental to how sediment moves through the ocean basins and how the geological record is constructed. Let your mind drift now through these concepts. Imagine sediment piling up at the edge of a continental shelf, layer upon layer, year after year, century after century. Feel the weight of it, the instability, and then the failure, the sudden rush of movement, the acceleration downslope. You're riding in the flow now, moving faster and faster, picking up more sediment, growing larger, feeling the canyon walls rush past on either side. The darkness is complete. The pressure builds as you descend deeper. The water temperature drops, but the flow continues, inexorable, driven by gravity and density, carving its way through the rock, building structures that will last for millions of years. And then, slowly, the slowing, the deposit beginning. The coarse particles settling first, then the finer ones, until finally you drift in suspension, a tiny clay particle in the dark water, taking days to settle the last 1,000 meters to the seafloor. And when you finally touch down, you're part of the sediment now, part of the geological record, a tiny piece of a vast deposit that records a single event, a single flow, one moment in the long history of submarine canyons. While there are thousands of submarine canyons scattered across the world's oceans, a few have become particularly well known, either because of their extraordinary size, their proximity to research institutions, or their unique characteristics. Let's descend into some of these famous canyons, exploring what makes each one special. Monterey Canyon, often called the Grand Canyon of the Pacific, lies just offshore of Monterey Bay in California. Its head begins at Moss Landing, a small coastal town where the canyon approaches to within just a few hundred meters of the shore. From there it extends more than 470 kilometers westward into the Pacific Ocean, reaching depths exceeding 4,000 meters on the abyssal plain. The canyon is 12 kilometers across at its widest point, with walls that rise up to 1,700 meters from the canyon floor. To put that in perspective, those walls are higher than the tallest building in the United States. If you could drain the water out of Monterey Bay and look into the canyon, you'd see a chasm comparable in scale to the Grand Canyon itself. What makes Monterey Canyon particularly special is its accessibility to scientists. The Monterey Bay Aquarium Research Institute is located in Moss Landing, right at the canyon head. This means that research vessels can reach depths of over a mile in just 2.5 hours of transit time, making the deep ocean accessible in a way that it isn't for most research institutions. Scientists from Mbari have conducted hundreds of dives into the canyon using remotely operated vehicles, documenting its geology, its biology, its ever-changing seafloor. They've watched turbidity currents reshape the canyon in real time. They've discovered new species living on the canyon walls. They've mapped the intricate network of channels and tributaries that feed into the main canyon. No other submarine canyon on Earth has been studied as intensively as Monterey Canyon. The canyon began to form millions of years ago, possibly as a river channel carved by the ancestral Salinas River during periods of lower sea level. Tectonic activity along the Pacific Plate may have also played a role, creating fault lines and zones of weakness where erosion could proceed more easily. But the canyon we see today has been shaped primarily by turbidity currents. Sediment from beaches near Moss Landing, carried by coastal currents, accumulates at the canyon head. This sediment is mostly sand and gravel, coarse material that gets destabilized by storm waves, by seismic activity, or simply by the sheer volume of accumulated material. When it fails, it creates turbidity currents that flow down the canyon axis, carving the granite bedrock at speeds that have been measured at more than 16 miles per hour. Turbidity currents in Monterey Canyon occur more than once per year in the upper reaches of the canyon. They're most common in winter when storm waves are strongest and when sediment transport along the coast is most active. Some currents travel the entire length of the canyon, eventually depositing their sediment load on the Monterey Deep Sea Fan, a massive accumulation of sediment at the canyon's mouth. Others peter out farther up the canyon, depositing their material in temporary storage until the next flow comes along to move it farther downslope. The canyon is a dynamic conveyor belt, constantly transporting sediment from the coast to the deep sea. The canyon's walls are home to a rich community of marine life. Deep sea corals cling to rocky outcrops, sponges filter nutrients from the water, fish shelter in the complex topography. The regular influx of sediment and organic matter from the surface creates a food-rich environment that supports far more life than the surrounding deep sea. Monterey Canyon is a biodiversity hotspot, a place where life concentrates and thrives despite the darkness, the cold, and the pressure. Across the continent, on the Atlantic coast, lies Hudson Canyon, the largest shelf-sourced submarine canyon on the east coast of the United States. Hudson Canyon begins at the edge of the continental shelf, off the coast of New York and New Jersey, where it captures sediment from the ancient path of the Hudson River. The canyon extends more than 60 kilometers in length and reaches depths of over 750 meters, with walls that rise up to 1,200 meters in some places. From there, it continues down the continental rise for approximately 450 kilometers, eventually reaching the Hatteras abyssal plain at depths exceeding 5,000 meters. Hudson Canyon, like many Atlantic canyons, was deeply influenced by the ice ages. During the last glacial maximum, when sea levels were more than 100 meters lower than today, the Hudson River flowed directly into the canyon head. The river delivered massive volumes of sediment, widening and deepening the canyon through a combination of direct erosion and triggered turbidity currents. Today, with sea levels higher, the canyon head is more than 100 kilometers from the current mouth of the Hudson River, but the canyon remains active. Sediment reaches the canyon through a variety of mechanisms: longshore drift, offshore transport during storms, and the occasional turbidity current triggered by the destabilization of sediment accumulated on the shelf. What makes Hudson Canyon particularly important is its role as a biodiversity hotspot and fishing ground. The canyon is recognized as a commercial fishing hotspot, containing essential habitat for numerous species of finfish, squid, and shellfish. Species like summer flounder, black sea bass, tilefish, longfin squid, lobster, and deep-sea red crabs all congregate in or near the canyon. Fisheries independent surveys have shown that certain managed species occur at much higher densities in the canyon than on the surrounding shelf. The canyon funnels nutrients, concentrates organic matter, and creates the complex topography and habitat diversity that marine life needs. Marine mammals are also drawn to Hudson Canyon. Concentrations of krill, a crucial food source, attract cetaceans including whales and dolphins. The canyon's productivity ripples up through the food web, supporting species at every level from tiny zooplankton to the largest predators in the ocean. Deep-sea corals have been found in Hudson Canyon as well, creating three-dimensional structures that provide even more habitat for fish and invertebrates. Some of these coral communities may merit special protection under federal conservation laws, though more survey work is needed to fully document their extent. Far across the Atlantic, off the western coast of Africa, lies the Congo Canyon, the world's largest submarine canyon in terms of the volume of sediment it transports. The Congo Canyon begins at the mouth of the Congo River, the second largest river in the world by discharge volume. Unlike most submarine canyons, which are separated from their source rivers by the continental shelf, the Congo Canyon directly intercepts the Congo River's flow. Sediment from the river pours directly into the canyon head, creating almost continuous turbidity currents that flow down the canyon and out onto the abyssal plain. The Congo Canyon extends for 800 kilometers across the continental shelf and slope, reaching depths of over 4,000 meters. It transports an estimated 55 million tons of sediment per year from the African continent to the deep Atlantic. This makes it one of the most important sediment transport systems on Earth, rivaling even major rivers in terms of the amount of material moved. The turbidity currents in the Congo Canyon are some of the most frequent and powerful in the world, continuously reshaping the canyon and building one of the largest deep-sea fans known. Another remarkable canyon system is found off the coast of Ireland, Whitted Canyon. This canyon lies about 400 kilometers south of the Irish coast, completely detached from any land-based sediment source. For years, scientists assumed that such headless canyons, which don't extend across the continental shelf to capture river sediment, would be relatively dormant. There might be occasional turbidity currents, perhaps triggered by earthquakes or major storms, but nothing like the frequent flows seen in canyons like the Congo or Hudson. But when scientists deployed monitoring equipment in Whitted Canyon, they discovered something surprising. The canyon experiences powerful turbidity currents at speeds up to 5 to 8 meters per second, about as fast as flows measured in major land-attached canyons. And these flows happen frequently, about 6 times per year, far more often than anyone had predicted. The turbidity currents weren't triggered by major storms or earthquakes. Instead, they seemed to be driven by more subtle processes, probably related to seasonal variations in cross-shelf sediment transport. This discovery forced scientists to reconsider their understanding of submarine canyons. If even land-detached canyons like Whitted experience frequent, powerful turbidity currents, then the amount of sediment and organic carbon being transported through submarine canyons to the deep sea may be much larger than previously estimated. Given that there are more than 1,000 similar land-detached canyons around the world, the implications are significant for understanding global sediment budgets, carbon cycling, and deep-sea ecosystems. Each canyon is unique, shaped by its local geology, its proximity to sediment sources, its history of sea level changes and tectonic activity. But all share certain characteristics: the steep walls, the V-shaped profiles in their upper reaches, the evidence of erosion by flowing sediment, and all play crucial roles in connecting the shallow coastal ocean to the deep sea, creating pathways for the movement of material and energy, providing habitat for countless species of marine life. To truly understand submarine canyons, we need to appreciate the nature of turbidity currents in more detail. These flows are the artists that sculpt the canyons, the conveyors that transport sediment, the architects of the deep-sea landscape. Yet they occur underwater, often in complete darkness, at depths where the pressure would crush any unprotected observer. They are, in many ways, invisible forces shaping an invisible world. When a turbidity current begins its journey down a canyon, it typically starts with a relatively small volume of failed sediment. This initial failure might involve just a few cubic meters or perhaps a few cubic kilometers of material. The sediment mixes with seawater, creating a dense suspension. Because this mixture is denser than the surrounding seawater, it begins to flow downslope, accelerating under the force of gravity. As the current flows, it encounters more sediment on the canyon floor and walls. If the flow is moving fast enough, and if the sediment is loosely packed, the current can entrain this additional material. The turbulent motion of the flow stirs up sediment, lifting it into suspension and incorporating it into the moving mass. This is where the positive feedback process begins. More sediment means higher density. Higher density means faster flow. Faster flow means more erosive power, and the ability to entrain even more sediment. The current grows sometimes exponentially as it races down the canyon. But turbidity currents are not uniform flows. Recent observations have revealed a complex internal structure. Many currents have a dense basal layer that moves along the seafloor, remobilizing sediment through a process that may involve liquefaction of loose packed sand. Above this dense layer is a more dilute suspension of finer particles. The dense basal layer acts like the front of a traveling wave, maintaining a relatively constant speed even as it erodes large volumes of material. The dilute layer above moves somewhat faster, with turbulent eddies and mixing along the interface. This structure has important implications for how canyons evolve. The dense basal layer is responsible for most of the erosion, carving the canyon deeper and wider. The dilute layer above transports finer sediment over longer distances. Together they create the distinctive morphology of submarine canyons, deep axial channels, where the dense layer concentrates its erosive power, terraces and levees, where sediment escapes from the main flow, and fans at the canyon mouth where the current finally slows and deposits its load. The seafloor in submarine canyons is often covered with distinctive bedforms that record the passage of turbidity currents. Crescent-shaped features called cyclic steps are common in sandy canyons. These bedforms form when the flow becomes supercritical, meaning it's moving faster than the speed at which disturbances can propagate through the fluid. This creates instabilities that lead to rhythmic patterns of erosion and deposition, producing trains of bedforms that migrate upslope over time. The bedforms are typically 1 to 3 meters high with wavelengths of 20 to 80 meters, giving the canyon floor a distinctly rippled appearance. Turbidity currents don't just shape the canyons themselves, they also build massive sedimentary structures at the mouths of canyons called deep-sea fans or submarine fans. These are analogous to alluvial fans on land, where rivers deposit their sediment load as they emerge from a canyon onto a plain. In the ocean, when a turbidity current exits the confining walls of a canyon and flows out onto the relatively flat abyssal plain, it spreads out and slows down. The coarsest sediment deposits first, close to the canyon mouth. Finer material travels farther before settling. Over time, repeated turbidity currents build up thick sequences of sediment, creating fan-shaped deposits that can extend for hundreds of kilometers from the canyon mouth. The Monterey Deep-Sea Fan, for example, is one of the largest sediment accumulations on the Pacific coast of North America. It has been built up over millions of years by countless turbidity currents flowing down Monterey Canyon. The fan contains layers of sand, silt, and clay, each layer representing a single flow event. By studying these layers, scientists can reconstruct the history of turbidity current activity in the canyon, learning about the frequency of flows, their magnitude, and how they've changed over time in response to climate change, sea level variations, and tectonic activity. One of the most fascinating aspects of turbidity currents is their role in global biogeochemical cycles. These flows don't just transport inorganic sediment, they also transport organic carbon, the remains of plants and animals from the surface ocean and from coastal environments. This organic carbon would normally decompose near the surface, releasing carbon dioxide back into the water and atmosphere. But when it's rapidly buried by turbidity currents and incorporated into deep-sea sediments, it can be sequestered for millions of years, effectively removing carbon from the active carbon cycle. Scientists estimate that turbidity currents are responsible for burying significant amounts of organic carbon in the deep sea. The exact amount is difficult to quantify because we still don't know how often turbidity currents occur in most canyons or how much organic material they carry. But the potential climate implications are substantial. Submarine canyons and turbidity currents may be one of the mechanisms by which the ocean regulates atmospheric carbon dioxide over geological timescales, making them important players in Earth's climate system. Turbidity currents also pose hazards to human infrastructure. The ocean floor is crisscrossed with submarine cables that carry more than 95% of global internet and telecommunications traffic. Many of these cables cross submarine canyons. When a large turbidity current flows down a canyon, it can break these cables, disrupting communications. The 1929 Grand Banks event broke multiple telegraph cables. More recently, earthquakes have triggered turbidity currents that damaged fiber optic cables in various locations around the world. Understanding turbidity currents, predicting when and where they might occur, is important not just for science but for maintaining the global communications infrastructure on which modern society depends. Let yourself drift now on currents of thought, moving slowly through these underwater valleys, feeling the weight of water above you, the pressure of the deep. The turbidity currents we've described might sound dramatic, even violent, but remember they happen in slow motion from a geological perspective. A single current might last hours or days. The canyon it carves might take millions of years to reach its current form. There's a patience to these processes, a steadiness to the sculpting of stone by flowing sediment. It's a dance of matter and energy, played out in darkness and cold, continuing year after year, century after century, shaping the hidden contours of the ocean floor. One of the most remarkable aspects of submarine canyons is their biological richness. Despite being located in the deep sea, an environment often described as a desert due to its scarcity of food and energy, submarine canyons are biodiversity hotspots. Life concentrates in canyons in densities that can be 50 to 100 times higher than in the surrounding deep sea floor. Some canyons support such abundant communities that they've been compared to rainforests or coral reefs in terms of their ecological importance. Why are canyons so much richer in life than other deep-sea habitats? The answer lies in several interconnected processes that make canyons special. First, canyons act as conduits for organic matter from the surface and from coastal areas. Phytoplankton that die in the surface waters normally sink slowly, decomposing as they fall, with only a small fraction reaching the deep sea floor. But in submarine canyons, organic matter can be transported rapidly to the depths by turbidity currents and by dense water cascades, reaching the canyon floor while still relatively fresh and nutritious. This creates a much richer food supply than is available in adjacent deep-sea areas. Second, canyons create upwelling conditions. The complex topography of canyons, with their steep walls and narrow confines, interacts with ocean currents in ways that promote the upward movement of deep water. This upwelling brings nutrient-rich water from the depths toward the surface, where it can fuel phytoplankton growth in the sunlit waters above the canyon. The increased primary production at the surface then provides more food that can settle down into the canyon, creating a positive feedback loop. Third, canyons provide habitat heterogeneity. The steep walls, rocky outcrops, sandy bottoms, and complex three-dimensional structure create a variety of microhabitats. Some species prefer hard substrates where they can attach. Others need soft sediments where they can burrow. Some thrive in areas with strong currents that bring food. Others prefer calmer conditions. The diversity of habitats within a canyon allows a diversity of species to coexist, each finding the particular conditions it needs. Studies in the Kaikoura Canyon off New Zealand revealed benthic biomass values that were 100 times higher than previously reported for non-chemosynthetic deep-sea habitats below 500 meters depth. The canyon floor was literally carpeted with live sea cucumbers, brittle stars, sea stars, mollusks, and numerous other invertebrates. In some areas, the biomass was so high that you could hardly see the seafloor beneath the animals. This wasn't isolated to a small area either. Large portions of the canyon supported these incredibly dense communities. Other canyons show similar patterns. The La Jolla Canyon off Southern California has been shown to have up to 50 times the biomass of surrounding shelf and slope areas. Even this remarkable number might be an underestimate because it doesn't account for mobile species that move in and out of the canyon, or for the small organisms living within the sediments that are harder to sample. The biological richness of canyons extends throughout the water column, not just on the seafloor. A study in the California current ecosystem found that 76% of krill hotspots occurred within and adjacent to submarine canyons. Krill are small crustaceans that are a crucial food source for many larger animals, including fish, seabirds, and whales. The concentration of krill in and near canyons creates feeding opportunities for top predators. Blue whales, humpback whales, various species of dolphins, seabirds, and fish all congregate near canyons to take advantage of the abundant food. The physical processes within canyons help explain these krill hotspots. Canyons disrupt the normal flow of ocean currents. When currents encounter a canyon, they can be channeled, accelerated, and deflected in complex ways. This creates areas of enhanced mixing, upwelling, and nutrient delivery. The combination of topography and currents creates fronts and eddies, dynamic features that concentrate plankton. Krill aggregate in these areas and predators follow. What's particularly interesting is that not all canyons are equally productive. The canyons that support the most persistent krill hotspots tend to be large shelf-incising canyons, the ones that cut deeply into the continental shelf and directly connect to coastal processes. These canyons are best positioned to intercept nutrient-rich coastal upwelling, to receive organic matter from rivers and coastal zones, and to create the strong current interactions that lead to plankton aggregations. Smaller canyons and those that don't extend far onto the shelf still support more life than the surrounding deep sea, but they don't reach the same levels of productivity as their larger cousins. The ecological importance of submarine canyons extends beyond their direct provision of habitat and food. Canyons may serve as stepping stones or corridors for species dispersal. A lava released in one canyon might drift with currents to another canyon many kilometers away, maintaining genetic connectivity between populations. Canyons may also serve as refugia during periods of poor ocean productivity. When conditions in the surrounding ocean are harsh, species might retreat to canyons where food is more reliable and habitat more diverse, surviving there until conditions improve. Some species appear to be canyon specialists, found almost exclusively in submarine canyon environments. Others are more generalist, but reach much higher densities in canyons. The communities vary from canyon to canyon depending on depth, oceanographic conditions, sediment type, and regional species pools. But across all canyons in all oceans, the pattern holds: canyons support more life, more diversity, more biomass than the surrounding deep sea. This biological richness has not gone unnoticed by commercial fisheries. Many of the world's most productive fishing grounds are associated with submarine canyons. Species that aggregate in canyons are targeted by both commercial and recreational fishers. While this provides economic benefits and food resources, it also raises conservation concerns. The species that congregate in canyons may be particularly vulnerable to overfishing because they're concentrated and predictable. The habitats within canyons, especially deep-sea coral and sponge communities, can be damaged by bottom trawling and other fishing gear that contacts the seafloor. There's growing recognition that submarine canyons merit special conservation attention. Some canyons have been included in marine protected areas. The Monterey Bay National Marine Sanctuary protects portions of Monterey Sokol and other canyons. Various deep-sea canyon systems off the Atlantic coast have been proposed for protection due to their importance for deep-sea corals and fish populations. In Europe, the European Marine Strategy Framework Directive has prompted assessments of canyon ecosystems with an eye toward protection and sustainable management. But conservation efforts are hampered by the simple fact that we know so little about most submarine canyons. It's hard to protect what you haven't studied, what you haven't mapped, what you haven't seen. This brings us to one of the central paradoxes of submarine canyon research. These features are incredibly important ecologically and economically. They cover huge areas of the ocean floor, yet only about 8.5% of known submarine canyons have been studied by the scientific community. More than 9,000 canyons exist. Only a few hundred have been explored in any detail. The rest remain mysteries, dark valleys beneath the sea, known only as lines on a bathymetric map. Among the most spectacular inhabitants of submarine canyons are deep-sea corals. These are not the colorful reef-building corals you might imagine from tropical waters. Deep-sea corals don't depend on sunlight and don't have the symbiotic algae that give shallow water corals their colors and much of their energy. Instead, deep-sea corals are animals that feed by capturing small particles and plankton from the water, using their tentacles to bring food to their mouths. They grow slowly, sometimes taking centuries to reach their full size, building intricate three-dimensional structures that provide crucial habitat in the otherwise relatively featureless deep-sea landscape. Scientists have discovered more species of deep-sea corals than shallow water species. This might seem surprising, but it makes sense when you consider that the deep sea covers a much larger area than tropical coral reef habitats, spans a much greater range of conditions, and has been around in one form or another for much longer. Deep-sea corals are found from the Arctic to the Antarctic, in all the world's ocean basins, at depths ranging from a few tens of meters down to more than 6,000 meters. They occur on continental shelves and slopes, on seamounts, on mid-ocean ridges, and especially in submarine canyons. Canyons provide ideal conditions for deep-sea corals. The steep walls offer hard substrate for attachment, which many coral species need. The strong currents that funnel through canyons bring a steady supply of food particles. The complex topography creates areas with different current speeds, allowing different species to find the conditions they prefer. Some corals like fast currents that bring lots of food. Others prefer calmer areas where they can spread their feeding tentacles without being damaged by water movement. The coral communities in submarine canyons can be extraordinarily diverse. In some canyons, scientists have found dense aggregations of octocorals like sea pens, soft corals, and gorgonians. These corals are colonial, made up of many individual polyps connected by soft tissue. They often have a branching or fan-like structure that maximizes their surface area for feeding. In other canyons, stony corals dominate. These are closer relatives to the reef-building corals of tropical waters, but they live solitary lives or form small colonies rather than building massive reef structures. One of the most remarkable deep-sea corals is Desmophyllum pertusa, formerly known as Lophelia pertusa. This stony coral can form extensive reef systems even in the deep sea. While most deep-sea stony corals are solitary cup corals, each coral animal living alone, Desmophyllum pertusa is colonial. Multiple polyps connect to form branching structures, and these structures can accumulate over time to build reefs. Some deep-sea Desmophyllum reefs are hundreds of miles long and rise more than 100 feet off the seafloor. One of the largest known deep-sea coral reefs was discovered off the coast of the southeastern United States, stretching over 300 miles from Miami, Florida to Charleston, South Carolina. In submarine canyons, Desmophyllum pertusa often grows on ledges and in areas where current speed is moderate. The corals form white, branching colonies that provide shelter for fish, crustaceans, mollusks, and countless other invertebrates. A single large coral colony might be home to hundreds of individual animals representing dozens of species. When scientists survey these coral habitats with remotely operated vehicles, the camera lights reveal a bustling community, fish darting between coral branches, crabs picking through the structure, looking for food, sea stars climbing slowly across the surface, brittle stars with their long, sinuous arms waving in the current. Gorgonian corals, also called octocorals or soft corals, are particularly abundant in many canyons. These corals have a flexible internal skeleton made of protein, sometimes reinforced with calcium carbonate spicules. They can bend with the current rather than breaking, making them well suited to areas with variable flow. Some gorgonians grow to enormous sizes. Paragorgia arborea, the bubblegum coral, can reach heights of 2 to 3 meters with thick branches that look remarkably like the branches of a terrestrial tree. Primno species form red or orange tree-like colonies that provide similar three-dimensional structure. In some canyons, entire coral forests develop, with large gorgonians dotting the landscape like trees in an underwater park. These coral gardens support high biodiversity and high biomass. The three-dimensional structure creates habitat complexity. Animals can live on the coral surface, within the branches, underneath the colony, in the shelter it provides. Young fish use coral colonies as nursery habitat, finding protection from predators among the branches. Invertebrates attach to coral skeletons or live commensally with the corals. Some species are found almost exclusively in association with corals, depending entirely on the habitat these animals create. But perhaps the most magical aspect of deep-sea corals in submarine canyons is that many of them can produce their own light. Bioluminescence, the production of light by living organisms, is incredibly common in the deep sea. An estimated 76% of deep-sea animals can bioluminesce, and many deep-sea corals have this ability too. The study of bioluminescence in deep-sea corals is still relatively young, but it has already revealed fascinating patterns. Scientists have confirmed bioluminescence in approximately 60 species of octocorals, including bamboo corals, sea pens, and various soft corals. Many more species likely have this ability, but haven't been tested yet. When physically or chemically stimulated, these corals emit light, usually in the blue or green wavelengths that travel farthest through seawater. The bioluminescence in octocorals involves a chemical reaction using an enzyme called luciferase. This is the same type of enzyme used by fireflies, though the specific molecular details differ. When stimulated, often by being touched or disturbed, the coral polyps emit a wave of light that travels through the colony. It's like a living light show in the darkness of the deep sea. Why would a coral bioluminesce? In the deep sea, where sunlight never penetrates, bioluminescence is one of the primary forms of communication. For a stationary animal like a coral, the most likely function is defense. If a predator, perhaps a fish or a sea star, attempts to feed on the coral, the sudden flash of light might startle it, or the light might attract a larger predator that could chase off or eat the initial attacker, a strategy sometimes called a burglar alarm. The light could also advertise to potential predators that the coral is toxic or unpalatable, a visual warning signal in an environment where other warning signals like bright colors would be invisible. Recent research suggests that bioluminescence in corals is ancient, dating back at least 540 million years to around the time of the Cambrian explosion, when animal life diversified rapidly in the oceans. By mapping the presence of bioluminescence onto the evolutionary tree of octocorals and comparing it to fossil evidence and molecular clock estimates, scientists determined that the common ancestor of all modern octocorals likely had the ability to bioluminesce. This means that for more than 500 million years, corals have been lighting up the deep sea, communicating through the darkness in a language of light. Imagine drifting through a submarine canyon in a submersible, your lights off to avoid disturbing the animals. The water around you is perfectly black. No light penetrates from above, no light emanates from below. But then, as the submersible gently bumps a coral colony, suddenly the coral blazes with light, a wave of blue-green luminescence spreading through the colony like electricity through a network. The light fades after a few seconds, and darkness returns. But the image remains, a reminder that the deep sea is not a dead, dark place, but a realm of hidden wonders, of light in darkness, of beauty in the abyss. These coral gardens are fragile. Many deep-sea corals grow incredibly slowly, perhaps only a few millimeters per year. A large Gorgonian coral 2 meters tall might be several hundred years old. Some coral colonies have been dated to over 4,000 years old, making them among the oldest living organisms on Earth. When these corals are damaged by fishing gear dragged across the seafloor, by sediment disturbance, or by climate change impacts like ocean acidification, they may never recover in human timescales. A coral garden that took 1,000 years to develop can be reduced to rubble in a single pass of a bottom trawl. Scientists and conservationists are working to identify and protect the most important coral habitats in submarine canyons. This requires mapping the canyons to understand their topography, surveying them with cameras and submersibles to document what lives there, and then developing management measures that can protect these ecosystems while still allowing sustainable use of marine resources. It's challenging work, made more difficult by the simple fact that the deep sea is so hard to access and study, but the effort is worthwhile. These coral gardens are unique ecosystems, irreplaceable on human timescales, harboring biodiversity and ecological complexity that we're only beginning to understand. Beyond the corals, submarine canyons host an astonishing diversity of other organisms. Fish are particularly abundant in many canyons. Species that live on or near the bottom, called demersal fish, find shelter and food in the complex topography. Rockfish, hack, grenadiers, and many others concentrate in canyon habitats. Some species spend their entire lives in canyons. Others visit seasonally or move in and out depending on food availability and environmental conditions. Invertebrates are everywhere in canyons. Sea cucumbers crawl across the seafloor, processing sediment and organic matter. Brittle stars with their long, flexible arms hide in crevices and under rocks, emerging to feed when conditions are favorable. Sea stars move slowly across surfaces, using their tube feet to capture prey or scavenge dead organisms. Crustaceans abound: crabs, lobsters, shrimp of many species, each filling a particular ecological niche. Mollusks are well represented too. Octopuses hunt in the canyon shadows. Squid hover in the water column, darting in to catch prey. Snails and limpets graze on organic films coating rocks. Bivalves filter food from the water or burrow in sediments. Some species of deep-sea mussels and clams live at cold seeps in canyon floors, places where methane and other chemicals seep out of the sediments. These chemosynthetic communities don't depend on sunlight at all, but derive their energy from chemical reactions, creating oases of life in the deep sea. Marine mammals regularly visit submarine canyons. Whales in particular are drawn to canyons because of the concentrated food resources. Sperm whales dive to great depths to hunt squid in canyon habitats. Beaked whales, some of the most mysterious and poorly known marine mammals, are often associated with canyons. Humpback whales and blue whales feed in waters above canyons where krill concentrate. Even dolphins and porpoises may visit canyons, following prey species or seeking out the unique oceanographic conditions. One particularly fascinating discovery in Barkley Canyon off Vancouver Island involved zooplankton migration. Scientists using a cabled observatory were able to monitor the canyon continuously for years, recording data every second. They discovered that large copepods, small crustaceans called neocalanus, migrate as deep as 1 kilometer into the canyon to complete their reproductive cycle. These animals typically live in surface waters, but they descend to depth to reproduce and then die, their bodies sinking and providing food for deep-sea communities. The ability to observe this behavior continuously, rather than through occasional shipboard sampling, revealed patterns that had never been seen before. The sediments in canyon floors also host rich communities of organisms, though these are less visible and less often studied. Worms burrow through the sediments, mixing them and aerating them. Tiny crustaceans move through spaces between sediment grains. Bacteria and archaea, single-celled organisms, process organic matter and nutrients. These microscopic communities are crucial for biogeochemical cycling, breaking down complex organic molecules and releasing nutrients back into the water where they can be taken up by other organisms. What's particularly remarkable is how interconnected these communities are. The deep-sea corals provide habitat for fish and invertebrates. The fish eat smaller invertebrates, and in turn become prey for larger predators or for visiting marine mammals. The invertebrates feeding on the seafloor are eaten by fish and crabs. Dead organisms sink and are consumed by scavengers or decomposed by bacteria. Organic matter from the surface ocean and from coastal areas flows down through the food web, supporting life at every level. The concentration of life in submarine canyons creates what ecologists call trophic hotspots, places where the flow of energy through the food web is enhanced. These hotspots are important, not just for the species that live in canyons, but for entire ocean basins. Canyons export biomass and productivity to surrounding areas. Fish that feed in canyons may be caught by fisheries in nearby shelf waters. Larvae produced in canyons may settle in other habitats. The nutrients cycled through canyon ecosystems are eventually distributed more widely. Canyons, despite being relatively small in area compared to the vast open ocean, punch above their weight in terms of ecological importance. Migration patterns of many species follow networks of submarine canyons. A whale might move from one canyon to another along a coastline, stopping to feed at each. Seabirds might follow canyon systems offshore, diving to catch fish and squid that concentrate in canyon waters. Even fish and invertebrates with limited mobility may move along canyon axes, following gradients of food, temperature, or other conditions. This network effect means that canyons can't be considered in isolation. Protecting one canyon is good, but protecting networks of canyons connected by migration routes and larval dispersal would be even better. Unfortunately, most marine protected areas are designed with political and jurisdictional boundaries in mind rather than ecological ones. A canyon might cross boundaries between state and federal waters or between the waters of different countries. Creating effective conservation measures requires coordination across these boundaries, which is challenging but necessary. The more we study submarine canyons, the more we realize how much we don't know. New species are discovered regularly. New ecological relationships are documented. New physical processes are measured. Each canyon seems to have its own character, its own community, its own story. And with 9,477 known submarine canyons on Earth, and only about 8% of them studied in any detail, there's a universe of discovery still waiting. Perhaps in a canyon somewhere right now, as you drift towards sleep, there's a species no human has ever seen. A coral glowing softly in the darkness. A fish species uniquely adapted to life on steep canyon walls. The ocean keeps its secrets well. Submarine canyons don't exist in isolation. They are part of a vast, interconnected system that links the coastal ocean to the deep sea, transports materials across ocean basins, and plays crucial roles in global biogeochemical cycles. Understanding canyons requires understanding their place in the larger ocean system. Canyons serve as the primary pathways for sediment transport from continental margins to the deep sea. Rivers deliver sediment to coastal areas. Coastal erosion contributes more material, but most of this sediment doesn't just accumulate on the continental shelf indefinitely. Instead, through the action of turbidity currents and other processes, it's funneled into submarine canyons and transported to the abyss. This process has been ongoing for hundreds of millions of years, ever since the continents took their current form and continental margins developed. The volume of material moved through canyons is staggering. The Congo Canyon alone transports an estimated 55 million tons of sediment per year. The Mississippi Canyon system, fed by one of the world's great rivers, moves enormous volumes of sediment from the North American interior to the Gulf of Mexico. Even smaller canyons without major river connections transport substantial amounts of material over geological time. Collectively, submarine canyons are responsible for much of the sediment that accumulates on abyssal plains, building vast deposits that record the history of erosion and deposition over millions of years. But sediment isn't the only thing canyons transport. They also move organic carbon, nutrients, pollutants, and even marine debris from shallow to deep waters. Organic carbon, the carbon contained in living organisms or in recently dead organic matter, is particularly important. In the surface ocean and coastal areas, organic carbon is produced by photosynthesis in phytoplankton, seaweeds, and coastal plants. Much of this carbon is respired back to carbon dioxide relatively quickly as organisms metabolize it. But when organic carbon is rapidly transported to the deep sea and buried in sediments, it can be removed from the active carbon cycle for millions of years. Scientists estimate that turbidity currents bury significant amounts of organic carbon in deep sea sediments. The exact numbers are still uncertain because we don't have good constraints on how much organic material is transported by turbidity currents, how much of it is preserved rather than decomposed, and how this varies between different canyons and different ocean basins. But the potential for submarine canyons to affect the global carbon cycle is substantial. If canyons are burying more organic carbon than we thought, they may be a more important carbon sink than previously recognized, with implications for understanding both the modern carbon cycle and past climate changes. Nutrients follow similar pathways. Nitrogen and phosphorus compounds, essential for life, are cycled through canyon ecosystems. Some nutrients are taken up by organisms, some are buried in sediments, some are released back into the water column through decomposition and remineralization. The balance of these processes determines whether canyons are net sources or sinks of nutrients for the surrounding ocean. Pollutants and marine debris also accumulate in canyons. Studies have found elevated concentrations of persistent organic pollutants like PCBs and DDT in fish collected from submarine canyons compared to fish from adjacent areas. This makes sense when you consider that canyons concentrate the flow of materials from coastal areas. Whatever is in the water or in coastal sediments can be transported down canyons, including contaminants from human activities. Marine debris, particularly plastics, has been found in canyon systems around the world. Bottom trawl marks, lost fishing gear, and other evidence of human activities are visible in videos from canyon surveys. The concentration of pollutants in canyons is concerning because these are also areas of high biological productivity and biodiversity. The same processes that make canyons good for life, the concentration of food and nutrients, also concentrate harmful substances. This creates a risk of bioaccumulation, where pollutants become increasingly concentrated as they move up the food web. A small amount of pollutant in the sediment might accumulate in worms. The worms are eaten by fish, concentrating the pollutant further. The fish are eaten by larger predators, and so on, until top predators like tuna or marine mammals might carry substantial burdens of pollutants originally introduced through canyon transport. On a more positive note, submarine canyons are increasingly recognized as crucial for maintaining ocean health and productivity. The upwelling they promote brings nutrients to surface waters, enhancing primary productivity in areas that might otherwise be relatively barren. The biodiversity they support contributes to ecosystem resilience and function. The habitats they provide, from coral gardens to soft sediment communities, are nurseries and refuges for commercially and ecologically important species. There's growing interest in using submarine canyons as natural laboratories for studying ocean processes. Because canyons concentrate so many phenomena, from turbidity currents to biological aggregations, they're ideal places to investigate how the ocean works. The cabled observatories in places like Barkley Canyon provide continuous data streams that reveal patterns invisible to traditional ship-based sampling. Repeated ROV surveys in canyons like Monterey document seasonal changes, episodic events like turbidity currents, and long-term trends in community composition. Climate change is adding new urgency to canyon research. As the ocean warms, as sea level rises, as currents shift and storm patterns change, how will submarine canyons respond? Will turbidity current frequency increase with more intense storms? Will species distributions shift as temperature zones move? Will changes in primary productivity in surface waters alter the food supply reaching canyon depths? These are open questions, but they're important ones. Submarine canyons are sensitive to changes in ocean conditions, and monitoring them could provide early warning signs of broader ecosystem shifts. The connectivity that canyons provide between shallow and deep ocean also means they may be corridors for invasive species or disease. A species introduced to coastal waters might be transported down a canyon and establish in the deep sea. A pathogen affecting coastal organisms might be carried to depths where it hasn't been present before. These are speculative scenarios for now, but they highlight how canyons link different parts of the ocean in ways we're still working to understand. As you drift deeper into rest, imagine the canyons as arteries of the ocean, great vessels carrying materials and energy from the surface to the depths. Picture the slow rain of particles settling through the water column, some reaching the abyssal plains, some caught by currents and funneled into canyons. See the organic matter, the remains of plankton and seaweeds, arriving at the canyon floor where it feeds communities of animals that have never seen sunlight. Feel the connections between surface and depth, between coast and abyss, between the world we know and the hidden world of the canyons. The frontiers of discovery. Despite more than a century of oceanographic research, submarine canyons remain among the least explored and least understood features on Earth. This might seem surprising. We've sent people to the moon, we've landed rovers on Mars, we've built a space station and telescopes that can see to the edge of the observable universe. Yet right here on our own planet, more than 90% of submarine canyons have never been explored by scientists. We know they exist from bathymetric maps, but we don't know what lives there, what geological processes are active, what unique features they might contain. Part of the reason for this gap in knowledge is simply the difficulty of deep-sea exploration. The ocean is vast, covering 71% of Earth's surface. Most of it is deep, with an average depth of about 3,800 meters. Working at these depths requires specialized equipment, ships, and submersibles. Manned submersibles can only stay down for a limited time and carry only a few people. Remotely operated vehicles extend our reach, but they're tethered to the ship by cables that limit their range and make them vulnerable to currents and entanglement. Autonomous underwater vehicles can survey large areas but carry less capable instruments. Ship time is expensive. A single day of research vessel operations can cost tens of thousands of dollars, A deep-sea expedition might involve weeks or months at sea, multiple research vessels, and teams of scientists and technicians. Funding for this work is limited and competitive. Most ocean research focuses on questions more directly related to human needs: fisheries, climate change, pollution, marine resources. Submarine canyons, while important, often aren't the top priority. But the situation is changing. New technologies are making deep-sea exploration more accessible and more affordable. Autonomous vehicles with longer battery life and better sensors can survey canyons without constant ship support. Improvements in sonar and imaging systems provide higher resolution data. Genetic techniques allow us to identify species from water samples without having to capture specimens. Cabled observatories provide power and data connections to instruments on the seafloor, enabling continuous monitoring that would be impossible with battery-powered systems. One of the most exciting recent developments is the use of environmental DNA, or eDNA. All organisms shed genetic material into their environment: skin cells, mucus, feces, reproductive cells. This DNA can be collected by filtering water samples and then sequenced to identify what species are present. In submarine canyons, eDNA surveys can reveal species diversity without the need for extensive visual surveys or physical sampling. A single water sample might contain DNA from dozens or hundreds of species, providing a snapshot of the community that's far more comprehensive than traditional methods could achieve in the same time. Citizen science is also beginning to play a role in deep-sea exploration. While most people can't visit submarine canyons personally, they can help analyze data. Projects like Seafloor Explorer ask volunteers to examine images from ROV surveys, marking interesting features and organisms. This crowdsourcing of data analysis allows researchers to process far more images than they could working alone, potentially revealing rare species or unusual phenomena that might otherwise be missed. Every new expedition to a submarine canyon reveals surprises. Species thought to be rare turn out to be common in the right habitat. Species believed to have narrow depth ranges are found far outside their known distributions. Completely new species are discovered. Behaviors never before observed are documented. The deep sea continually reminds us how much we have yet to learn. In the Mar del Plata Canyon off Argentina, a recent expedition documented coral reefs at 3,300 feet depth and meadows of soft coral near 4,900 feet. They found bright orange sea stars that looked like cartoon characters. They collected specimens of deep-sea limpets from rocky outcrops on the abyssal plain, discovering that these limpets represent species new to science. The canyon lies where two major ocean currents meet, creating swirling eddies and boundaries that concentrate food and create diverse microhabitats. In Mediterranean canyons, researchers have documented megafauna communities and assessed human impacts. They've found evidence of bottom trawling damage, visible scars on the seafloor where fishing gear has scraped away corals and other benthic organisms. They've also found areas of pristine habitat, coral gardens that have escaped damage, demonstrating what these ecosystems can be when protected. The contrast is striking and sobering. In canyons off Ireland, scientists measuring turbidity currents were surprised to discover how active these systems are. The conventional wisdom was that canyons far from land would be relatively dormant, but the monitoring data showed frequent powerful flows, completely changing our understanding of sediment transport in these systems. Each discovery raises new questions. How do organisms in canyons adapt to the episodic disturbance of turbidity currents? Some canyon species must be able to survive or escape these flows, or to rapidly recolonize after a flow passes. What are the genetic connections between populations in different canyons? Are canyon populations isolated, evolving independently, or is there gene flow through larval dispersal? How do communities assemble in canyons? Do species arrive in a predictable sequence, or is community composition more random? Climate change adds another layer of complexity and urgency. We know that ocean conditions are changing rapidly: warming temperatures, acidifying waters, decreasing oxygen levels in some regions, shifting current patterns. How will these changes affect submarine canyons? Will warming waters alter the species that can live in canyons? Will changes in surface productivity affect the food supply reaching canyon depths? Will altered storm patterns change the frequency of turbidity currents? We can't answer these questions without baseline data about current conditions, and for most canyons, we simply don't have that data. Some scientists argue that submarine canyons should be considered priority targets for marine conservation. They're biodiversity hotspots. They provide critical ecosystem services. They're vulnerable to human impacts. But protecting canyons effectively requires knowing where they are, what lives in them, what threats they face, and how different management strategies might affect them. This requires exploration, research, monitoring, all of which require resources and commitment. International cooperation is essential. Submarine canyons don't respect political boundaries. The same canyon might cross through waters controlled by different countries. The species that live in canyons may migrate across vast distances. Turbidity currents and ocean currents don't stop at borders. Effective conservation and management of canyon systems requires countries to work together, sharing data, coordinating policies, and developing common approaches. There's reason for hope. The global ocean community is increasingly recognizing the importance of submarine canyons. Major research initiatives are underway in various regions. International symposia bring together canyon researchers to share findings and coordinate future work. Some canyons have been designated as marine protected areas. Technologies for studying the deep sea continue to improve and become more accessible. But time is pressing. Human impacts on the ocean are accelerating. Deep sea fishing is expanding into deeper waters. Interest in deep sea mining is growing. Climate change is affecting even the most remote ocean regions. We're exploiting the ocean before we fully understand what's there, what it does, why it matters. Submarine canyons, like much of the deep sea, are being altered before they're even properly documented. The exploration of submarine canyons is not just a scientific endeavor. It's also a source of wonder and inspiration. The images that come back from canyon expeditions, the videos of bioluminescent corals and strange fish, the maps showing intricate topography, all remind us that Earth is still a planet of mysteries. There are places we've never been, creatures we've never seen, processes we've never witnessed. And those places, those creatures, those processes are right here in our ocean, waiting to be discovered. To truly appreciate life in submarine canyons, we need to understand the sensory world these creatures inhabit. It's a world fundamentally different from our own, where the senses we rely on most, sight above all, are often useless, and where other senses we barely possess or don't possess at all, become paramount for survival. In the perpetual darkness of the deep sea, vision as we know it has limited utility. There's simply no light to see by, no ambient illumination that would allow for the kind of vision we depend on. And yet many deep-sea animals do have eyes, sometimes quite elaborate eyes, adapted to detect the faintest glimmers of bioluminescence, or to make the most of what little light exists in the twilight zone, where the canyon opens to shallower water. Some deep-sea fish have enormous eyes relative to their body size, eyes that take up a substantial portion of their heads. These eyes are optimized for gathering every available photon of light, working at the absolute limits of what eyes can do. The lenses are large, the pupils are huge, the retinas are packed with rod cells, the photoreceptors specialized for low-light vision, with very few or no cone cells, which are responsible for color vision but require more light to function. In the deep sea, color vision would be useless anyway, because there's no spectrum of light to perceive, just occasional flashes of blue or green bioluminescence. Other deep-sea animals have lost their eyes entirely through evolutionary time. If eyes are expensive to maintain, requiring energy to build and operate, and if they provide no benefit in absolute darkness, then natural selection will favor individuals that don't waste resources on eyes. Some deep-sea fish are completely blind, their eyes reduced to tiny vestiges buried under skin, non-functional, but still present as evolutionary remnants. Some deep-sea shrimp and crustaceans are likewise blind, navigating their world through other senses entirely. Mechanoreception, the sensing of water movement and pressure changes, becomes crucial in the darkness. Many fish have a lateral line system, a series of sensory organs running along their sides that detect disturbances in the water. When something moves nearby, a prey item swimming past, a predator approaching, a turbidity current beginning, it creates pressure waves that propagate through the water. The lateral line detects these pressure changes, giving the fish a kind of distance touch, a way of sensing objects and events without direct contact. The lateral line is so sensitive that fish can detect the wing beats of a small crustacean from several body lengths away. They can sense the approach of a predator even in complete darkness. They can navigate through complex terrain, avoiding obstacles and finding pathways through boulder fields and coral gardens without ever seeing them. For a fish living on a canyon wall at 2,000 meters depth, where no light penetrates and bioluminescence is sporadic, the lateral line is perhaps the most important sense for moment-to-moment survival. Chemoception, the sensing of chemicals dissolved in water, is likewise essential. This is analogous to our senses of taste and smell, though the line between the two is blurred in water, since all chemicals are dissolved in the medium. Many deep-sea animals have highly developed chemoceptive abilities, able to detect incredibly low concentrations of specific molecules that signal food, mates, predators, or territory. A hagfish, that strange eel-like creature that scavenges on the deep-sea floor, can smell a dead whale from kilometers away. The whale's decomposing tissues release amino acids and other organic compounds that diffuse through the water. The hagfish detects this chemical plume and follows the concentration gradient upstream, swimming against the current, heading toward higher and higher concentrations until it reaches the source. This can take hours or days, but the reward, a massive food bonanza that might sustain the hagfish for months, is worth the journey. Lobsters and crabs use chemical cues to find food, to locate mates, and to recognize individuals. They taste the water constantly with chemoreceptors on their antennae and legs, processing a constant stream of chemical information about their environment. In laboratory experiments, crabs can distinguish between water that has flowed over a predator versus water that hasn't, and they adjust their behavior accordingly, becoming more cautious and alert when predator chemicals are detected. Some deep-sea animals use electroception, detecting the weak electrical fields that all animals produce through the action of their nerves and muscles. Sharks and rays are famous for this ability, possessing special organs called ampullae of Lorenzini that can detect electrical fields as weak as a few nanovolts per centimeter. This allows them to find prey buried in sediment or hiding in crevices, prey that makes no sound and emits no visible light but cannot hide its electrical signature. Some deep-sea fish have similar abilities, though the organs involved are different. They can detect the electrical activity of other fish or of invertebrates, using this sense to hunt in complete darkness. A fish might swim slowly over the seafloor, sweeping back and forth, until its electroreceptors detect the telltale signal of a buried worm or shrimp. Then it strikes, pinpointing the location with precision despite never having seen its prey. Touch, direct mechanoreception through contact, is another important sense. Many deep-sea animals have long, sensitive barbels or fin rays that extend from their bodies, acting like whiskers to explore their immediate surroundings. Grenadier fish, also called rattails, have long tapering bodies with sensitive pelvic fins that drag along the seafloor as they swim, constantly feeling for food items, for obstacles, for changes in substrate. When they detect something interesting, they turn and investigate more closely, perhaps eating it if it's food, perhaps fleeing if it suggests danger. Sea spiders walk slowly across surfaces on long legs, equipped with sensory hairs that detect texture, chemistry, and perhaps other stimuli we don't fully understand. Every step gives them information about the substrate they're walking on, about the presence of prey or suitable attachment sites for egg cases, about the local environment in tactile terms. Bioluminescence, as we've discussed, is a form of communication, a visual signal in a dark world, but it's more than just light. The pattern of flashing, the color, the duration, the intensity, all carry information. Some animals use bioluminescence to attract prey, dangling a glowing lure like an anglerfish's esker. Some use it to startle predators, creating a sudden flash that might cause a predator to hesitate just long enough for the prey to escape. Some use it for species recognition and courtship, creating species-specific patterns that say, "I'm the same species as you, and I'm ready to mate." Some deep-sea creatures engage in what's called counter-illumination. These animals have bioluminescent organs on their undersides that they can adjust to match the faint light coming from above. From below, a predator looking up would see a prey animal silhouetted against the slightly brighter surface water, making it easy to detect. But with counter-illumination, the prey matches its ventral surface brightness to the background, making itself effectively invisible from below. It's sophisticated camouflage, active camouflage, that requires constant adjustment as depth and ambient light levels change, and it works beautifully. Sound is another modality, though perhaps less important in canyons than in some other environments. Water is an excellent medium for sound transmission, much better than air. Sounds can travel for kilometers or even hundreds of kilometers through the ocean, depending on their frequency and the properties of the water. Some fish produce sounds using their swim bladders as resonating chambers, creating grunts, croaks, and other vocalizations. Some snapping shrimp create incredibly loud popping sounds by rapidly closing their claws, producing a cavitation bubble that collapses with a sharp report, loud enough to stun small fish. Whales, of course, are masters of underwater sound. Their calls can travel across entire ocean basins. Sperm whales diving into canyons to hunt squid use echolocation, producing series of loud clicks and listening for the returning echoes. The pattern of echoes tells the whale about objects in the environment, their distance, their size, their shape, perhaps even their composition based on the quality of the echo. A whale can essentially see with sound, building a sonic picture of its surroundings and hunting squid in total darkness with remarkable precision. For us, trying to imagine the sensory world of a deep canyon is a challenge. We are so visually oriented, so dependent on light, that it's hard to conceive of navigating, finding food, finding mates, avoiding predators, all without vision, or with vision so limited that it's only useful for detecting brief flashes of bioluminescence. But for the creatures of the canyons, this is normal. This is the world they evolved in, the world they're perfectly adapted to. The darkness isn't a problem, but simply reality. The pressure isn't crushing, but supportive. The cold isn't uncomfortable, but optimal. As you drift deeper into sleep, imagine experiencing the world through these other senses. Feel the water moving past you, detecting every ripple and eddy through sensors along your flanks. Taste the chemical traces in the water, following gradients toward food or away from danger. Sense the weak electrical fields of other creatures moving nearby, even in complete darkness. Let go of your dependence on vision, on light, and imagine instead a world of pressure, chemistry, electricity, vibration. It's a different kind of awareness, a different way of being alive, but it works beautifully in the environment where these creatures make their home. One of the most striking aspects of submarine canyon ecosystems is the range of timescales at which different processes occur. Understanding these timescales helps us appreciate both the dynamism and the stability of these systems, the ways in which they're constantly changing and yet somehow remaining fundamentally the same. At the shortest timescale, measured in seconds to minutes, individual organisms go about their immediate business. A fish strikes at a passing shrimp, the attack and capture taking perhaps a second. A coral polyp captures a small copod with its tentacles, pulling the food to its mouth over a few seconds. A brittle star detects a morsel of food drifting by and bends its arm to intercept it, the movement taking 10 or 20 seconds. A crab walks across the seafloor at a few centimeters per second, covering a meter in maybe 30 seconds. These are the moment-to-moment events of life, the feeding and moving and breathing that happen constantly. At a slightly longer timescale, measured in hours to days, we see larger patterns. The daily vertical migration of zooplankton, though this is less pronounced in the deep sea than in shallower water, still influences food availability in canyons. Some animals are more active at certain times, following circadian rhythms, even in the absence of light cues, possibly entrained by subtle pressure changes from tides, or by internal biological clocks that persist even without external cues. A fish might have a daily pattern of activity, even though every hour is equally dark. Turbidity currents operate on this timescale. A single flow event might last anywhere from a few hours to a few days from initiation to final deposition. During that time, the canyon is dramatically altered. The seafloor is scoured in some places and buried in others. Currents are disrupted, animals are killed or displaced, and then it's over, and the canyon begins to recover, to recolonize, to return to a semblance of its pre-flow condition. At the scale of weeks to months, seasonal patterns emerge, even in the deep sea. Changes in surface productivity, driven by seasonal variations in sunlight and mixing in temperate and polar regions, affect how much food rains down from above. Spring blooms in surface waters lead to increased food availability in the deep sea weeks or months later. As phytoplankton die and sink, some deep sea animals time their reproduction to match these seasonal pulses of food, though the mechanism by which they detect the seasons remains mysterious. Storms and oceanographic events like El Niño can influence canyon systems on this timescale. A major storm can trigger turbidity currents. Changes in coastal upwelling can affect nutrient delivery to surface waters above canyons, which in turn affects food supply to the depths. These events are irregular, but they're part of the natural variability that canyon ecosystems experience. At the scale of years, individual organisms show their life histories. A small rockfish hatches from an egg, spends its larval phase drifting in the plankton, settles onto a canyon wall, grows slowly, reaches sexual maturity after several years, and begins reproducing. A sea urchin grows its its hard shell, year by year, surviving predation and environmental fluctuations through some combination of luck and adaptation. Individual corals grow, adding new polyps and extending their branches, building the structure that will support the next generation of associated organisms. At decades to centuries, we see the lifespans of the longest-lived organisms. Some deep-sea fish live for decades, growing slowly, reproducing occasionally, accumulating years. Some corals live for centuries. A large Paragorgia arborea colony might be 200 or 300 years old, having started life when Mozart was composing symphonies or when the American Revolution was being fought. During that time, the coral has survived countless turbidity currents, periods of low and high food availability, and whatever other challenges the deep sea has presented. Some organisms live even longer. Orange ruffy, a deep-sea fish that's been heavily fished for food, can live for more than 100 years, with some individuals possibly reaching 150 years or more. They grow slowly and mature late, making them particularly vulnerable to overfishing, because a population can't recover quickly when depleted. Black coral, despite its name actually related to sea anemones and soft corals, can live for thousands of years. Some black coral colonies have been radiocarbon dated to more than 4,000 years old, making them among the oldest living organisms on Earth, older than the pyramids, older than written history, living witnesses to the rise and fall of civilizations that knew nothing of their existence. At the scale of millennia, we see ecosystem dynamics and evolution. Populations of organisms change in genetic composition as natural selection favors certain traits and disfavors others. New species arise through isolation and adaptation. Climate changes, including the glacial-interglacial cycles of the Pleistocene, alter ocean conditions in ways that affect deep-sea life. Sea levels rise and fall. Temperature profiles change. Ocean chemistry evolves. The species present in a canyon 10,000 years ago might not be quite the same as those present today, though many would be recognizable. At millions of years, we see canyon formation and evolution. The canyons themselves are being carved. Turbidity currents flow repeatedly down the same pathways, slowly cutting deeper into the continental slope. The canyons extend headward, capturing more of the sediment transported across the shelf. They broaden, deepen, develop tributaries and terraces and all the complex morphology we see in modern canyons. The process is slow by human standards, but relentless by geological standards. And at the scale of hundreds of millions of years, we see the largest changes. Continents move. Ocean basins open and close. Species arise and go extinct. The entire biological community turns over multiple times as evolution produces new forms and eliminates old ones. The canyons we see today are relatively young features in most cases, having formed primarily during the Cenozoic era, the last 66 million years since the extinction of the dinosaurs. But the processes that form them have been operating for much longer, probably as long as there have been oceans and continental margins. This multiplicity of timescales is dizzying to contemplate. At any given moment, processes are occurring at every scale, from the split-second movements of a hunting fish to the million-year evolution of canyon morphology. And all of these scales matter. The quick movements of organisms affect population dynamics, which affect ecosystem structure, which affects evolutionary pressures, which affect the long-term composition of communities. The slow processes of geology create the template on which biology plays out, the stage on which the drama of life in canyons unfolds. As you lie here on the edge of sleep, your own body is operating on multiple timescales. Your heart beats roughly once per second, a rhythm you can feel if you pay attention. Your breathing occurs on a scale of seconds, each breath in and out a cycle that brings oxygen and removes carbon dioxide. Your cells are metabolizing continuously, chemical reactions happening at astonishing speeds, enzymes catalyzing reactions thousands or millions of times per second. And yet your body also operates on longer time scales. The daily rhythm of activity and rest, the weekly and monthly patterns of life, the years of growth and maturity, the decades of a human lifespan. You're part of these nested cycles, these overlapping rhythms, and in a deep sense you're connected to the canyons too, not through any mystical link but through the physical reality of being part of Earth's systems. The oxygen you breathe was largely produced by ocean phytoplankton, some of which live in waters above submarine canyons. The calcium in your bones came ultimately from the weathering of rocks, some of which are now buried in canyon floors, transported there by turbidity currents. The water in your body has cycled through the ocean, evaporated into the atmosphere, fallen as rain, flowed through rivers, returned to the ocean, over and over across billions of years. Let these thoughts wash over you. The time scales, the connections, the vastness of geological time and the brevity of a single heartbeat. You're part of it all, temporary, and yet connected to processes that extend far beyond your individual existence. Rest now in that knowledge. Let time lose its urgency. Let yourself exist simply in this moment, breathing, resting, part of a universe that operates on scales from the infinitesimal to the infinite. As we drift toward the end of our journey through deep-sea canyons, let yourself settle even more deeply into rest. The canyons we've explored tonight are real places, existing right now in the dark depths of the world's oceans. While you rest, they continue their slow transformations. Sediment settles, currents flow, animals feed and reproduce and die. Corals grow, molecule by molecule. The ancient dance of geology and biology continues, as it has for millions of years, as it will for millions more. There's something deeply comforting about these hidden places. They remind us that the world is larger and more complex than our daily experience suggests, that there are realms beyond our immediate perception, operating on different timescales, following different rules. The canyons don't care about human concerns. They don't know about our politics, our worries, our plans. They simply exist, shaped by physical forces and inhabited by organisms, adapted to conditions we find almost unimaginable. The darkness of the canyons is not an absence but a presence. It's a darkness that has been there since before humans existed. A darkness older than our species, perhaps older than life itself. And within that darkness, life has found ways to flourish. Creatures make their own light. Corals filter nutrients from water they cannot see. Fish navigate by touch and sound and electrical sense. The darkness is not empty but full, not dead but alive, not hostile but simply different. The pressure of the deep likewise is not crushing but supporting. For organisms adapted to high pressure, it's normal, comfortable even. A deep-sea fish brought rapidly to the surface would suffer from the low pressure, just as we would suffer from the high pressure at depth. Each organism lives in the conditions it has evolved to tolerate, to thrive in. There's no one way for life to be. The canyons demonstrate this beautifully, hosting species that have taken evolutionary paths different from surface dwellers, finding solutions to problems we never have to face. The cold of the deep is a slow cold, a steady cold, unchanging across seasons and years. Surface waters warm and cool with the sun and the atmosphere. But in the depths, temperature is constant, hovering just a few degrees above freezing year-round. For animals living there, this constancy is predictable, reliable. They don't have to adapt to changing conditions. They can specialize, optimizing their physiology for one set of conditions and living there indefinitely. And the time scale of the canyons is worth contemplating. A turbidity current might last hours or days, but the canyon it carves has been developing for millions of years. A coral colony might be centuries old, having grown through human history. The sediments accumulating on canyon floors contain records going back millions of years, each layer a moment frozen in time, a record of what fell from above, what lived in the sediments, what conditions were like when that layer was the surface. We move so quickly through our lives, measuring time in minutes and hours and days, but the canyons remind us of deeper time, geological time, evolutionary time. They remind us that the present moment is just one point in a continuum, stretching back billions of years to the formation of Earth and forward billions more to whatever future awaits our planet. In this context, our individual concerns, our daily stresses seem smaller. not unimportant, but proportioned differently. You are part of a planet, part of an ocean system, part of a web of life that includes coral polyps glowing in submarine canyons and krill swarming in upwelling waters. The atoms in your body were forged in stars, cycled through Earth systems, and will continue cycling long after your lifetime. You are ancient and temporary all at once. A brief configuration of matter that can think and feel and wonder about submarine canyons. The canyons are there right now. Off the coast of California, sediment is accumulating at the head of Monterey Canyon, preparing for the next turbidity current. Off the coast of Africa, the Congo River pours sediment into its canyon, day and night, continuous, tireless. Off the coast of Ireland, currents swirl through Whitted Canyon, bringing nutrients to corals clinging to its walls. Off the Atlantic coast, fish congregate in Hudson Canyon, feeding, resting, following ancient patterns. All of this is happening now, as you rest, as you let go, as you drift into sleep. The ocean is vast, the canyons are numerous, the life they support is diverse and abundant, and almost all of it is unknown to us, unseen, unexplored. This is humbling. It reminds us how much there is still to discover, how limited our knowledge is, how much of Earth remains mysterious despite all our technology and science. But it's also hopeful. If submarine canyons can be so rich with life despite the darkness and cold and pressure, if coral gardens can flourish miles beneath the surface, if species can evolve and adapt to conditions that seem impossible, then perhaps Earth is more resilient than we sometimes fear. Perhaps life is more tenacious, more creative, more persistent than we give it credit for. The canyons will be there tomorrow and next week and next year. They were there before humans, and barring some global catastrophe, they'll be there after us. They are patient. They are enduring. They are monuments to the power of slow processes operating over vast time, to the creativity of evolution, to the persistence of life in every niche it can possibly occupy. Tonight, as you sleep, you can rest knowing that somewhere far beneath the surface of the ocean, in cold, dark waters under crushing pressure, there are valleys carved by flowing sediment, walls encrusted with ancient corals, fish hovering in currents, and creatures making their own light. The canyons are real, the life is real, the processes are ongoing, and they connect to you through the oxygen you breathe, much of it produced by ocean plankton, through the climate you experience, regulated in part by ocean processes, through the seafood you might eat, some of it from fish that spawned or fed in canyon systems. We are all part of the ocean, even those of us who never see it. The water in your body was once in the ocean. The elements in your bones were cycled through marine systems. We are, in a very real sense, made of ocean, and we remain connected to it through countless threads of chemistry and biology and physics. So rest now, knowing you're part of something vast and ancient. Let the knowledge of submarine canyons, of deep-sea corals, of bioluminescent displays in the abyss, wash over you like gentle currents. Let your breathing slow to match the patient time scale of canyons. Let your thoughts settle like sediment drifting to the seafloor. Let yourself sink into deep, peaceful rest, cradled by the knowledge that Earth is full of wonders, most of them hidden, all of them continuing their existence, whether we see them or not. The canyons are there, the ocean is there, and you are here resting, part of it all. Connected to everything, safe and supported like an animal in its habitat, sleeping now in the shelter of knowledge and wonder, drifting into dreams perhaps of deep blue water, of gentle currents, of light in darkness, of life flourishing in places we've only begun to explore. Sleep well, dream peacefully, and perhaps when you wake, you'll carry with you a sense of the vastness of Earth, the persistence of life, the quiet majesty of places like submarine canyons, hidden beneath the waves, supporting ecosystems we've barely glimpsed, continuing their ancient work, patient and enduring, in the deep. Good night.